Welcome back to The Deep Dive, the show where we take a stack of sources and really pull out the knowledge you need.
Okay.
Today we're tackling something fundamental, combustion, fire. We're going from, ancient fuels like wood, even cow dung,
Right. Things used for millennia.
all the way up to modern stuff. LPG, that's liquefied petroleum gas, and CNG, compressed natural gas.
And it seems simple on the surface, doesn't it? It's just fire.
Yeah.
But the details, the science behind it, well, that affects everything. How we cook, how we heat our homes.
Even how fast glaciers melt, which is kind of mind-blowing.
Exactly.
And the sources kick us off with a really great question, almost deceptively simple. Why does a candle burn with that nice, visible flame we all recognize? But coal, or say charcoal briquettes on a barbecue, often just glow red hot. No real flame there. What is going on?
That's the perfect starting point. That difference, that little paradox, is really the key to understanding the whole process of combustion.
So our mission today,
Well, it's to dig into the science, Why do some things make a flame? How does that knowledge help us fight, say, a big fire?
and then the big picture, what's the real environmental cost for all these different fuels we use every day?
Okay, let's get into it. The basics first. What even is combustion?
Right. At its core, it's a chemical process. You take a substance, the fuel they call it, or the combustible substance,
Yeah, fuel.
and it reacts with oxygen. And that reaction gives off heat. Simple enough.
Yeah.
And fuel can be solid, liquid, or gas.
And here's an aha moment right away, something the sources point out. This exact process, it's happening inside you right now.
Inside me. How?
Your food.
Yeah.
It's literally fuel for your body. It gets broken down, reacts with the oxygen you breathe.
To produce energy. Heat.
Precisely. It's basically a very, very slow, very controlled kind of combustion, just without the flames, thankfully.
Huh. Never thought of my lunch as combustion before.
Yeah.
Okay, so whether it's wood or my lunch,
Yeah.
you need air, oxygen. That's non-negotiable.
Absolutely critical. And there's a classic experiment that shows this perfectly. The candle and chimney one.
Right, I remember this from school. You put a glass chimney over a candle.
Uh-huh. If air can get in easily from the bottom, the candle flame burns steadily, nice and bright.
But then if you block the bottom, maybe lower the chimney right down onto the table.
Then the flame starts to, well, struggle. It flickers, it gets smoky, puts out that black soot.
Says it's starved for air.
Exactly, limited oxygen. And the final step. If you completely cut off the air, maybe put a glass plate right over the top of the chimney.
Poof, flame goes out. Instantly.
Instantly. Doesn't matter if the wick's hot or there's plenty of wax left. No oxygen, no combustion. Reaction stops.
Yeah.
Dead.
Okay, so that's lesson one for fire safety, isn't it? If someone's clothes catch fire,
You smother it, grab a blanket, a heavy coat, anything thick.
and you're not really cooling it down immediately,
Not primarily, you're cutting off the air. Denying the fire that essential oxygen it absolutely needs to keep burning, it's the fastest way to stop it.
right? So we need fuel, check. We need air, oxygen, check. But there's something missing. If I hold a match near, say, a log for just a second, nothing happens.
Good point. What's the missing piece?
There must be a third thing.
There is. It's the heat. But not just any heat. You need to reach what's called the ignition temperature.
Ignition temperature. Okay,
Yeah.
what's that defined as?
It's the minimum temperature, the lowest point at which that specific fuel will catch fire and keep burning on its own.
And that temperature must vary wildly, right? Like kerosene or petrol seem to catch fire so easily.
Very easily, just a little bit of heat is enough. But wood, or coal, needs a lot more sustained heat to get going.
So kerosene has a much lower ignition temperature than wood.
Exactly. Which is why things like petrol, alcohol, LPG, they're labeled inflammable substances. Their ignition temperature is very low, making them catch fire incredibly easily. Handle with care.
Okay, this ignition temperature thing. The sources have this fantastic demonstration. It sounds almost like a magic trick. The paper cup experiment.
Ah, yes, activity 4.4. It really makes you think. So take an empty paper cup, hold it over a candle.
Burns up almost instantly, right? Paper's flammable.
Of course. But now take the exact same kind of paper cup, pour in, say, 50 milliliters of water, just regular tap water,
Okay.
and hold that over the candle flame.
Does it just take longer to burn?
It doesn't burn, the paper doesn't catch fire, the water inside might get hot, it might even start to boil. But the paper cup itself stays intact.
Wait, seriously? Boiling water in a paper cup over a flame? How is that possible? Why doesn't the paper just ignite?
It's all about heat transfer. The heat from the flame hits the paper, but it's immediately pulled away, transferred into the water. Conduction.
Ah, so the water acts like a like a heat sink.
Exactly. It absorbs the heat so efficiently that the paper itself never gets hot enough to reach its own ignition temperature. It simply can't ignite while the water is there absorbing the energy.
That is genuinely cool. Physics in action. Okay, so we need that initial pick of heat to cross the ignition threshold. How do we usually get that day to day?
Well, historically and still today, the humble matchstick.
Right. How does that work? It's not just wood scraping on a box.
No. The modern safety match is a little chemical marvel. We don't need all the compound names. But the key is friction. When you strike the match,
That rubbing
it
action.
creates a tiny localized burst of heat just from the friction itself.
And that tiny bit of heat is enough.
It's enough to trigger a chemical reaction on the match head. Basically, that friction converts a safer chemical, red phosphorus on the box, into a much more reactive one, white phosphorus, just for an instant.
Okay.
That white phosphorus reacts immediately with another chemical in the match head, potassium chlorate, releasing enough heat to ignite the main fuel component, usually antimony trisulfide, and boom, the match flares up.
Wow. So friction provides the activation energy, essentially.
Yeah.
Just enough to hit that ignition temperature for those specific chemicals.
Precisely. A controlled way to start the fire.
But what about when fire isn't controlled?
Yeah.
When it gets out of hand? We need a way to think about stopping it.
That brings us to the fire triangle. Simple, but fundamental for firefighters.
Okay, what are the three sides? We've basically covered them.
It's fuel, air, specifically oxygen, and heat, which needs to be above that ignition temperature.
Got it. Fuel, air, heat.
Yeah.
You need all three for a fire to burn.
Correct. So to put a fire out, you have to break the triangle. You need to remove at least one of those three things.
Okay, that makes sense. And usually the fuel is the hard part to remove, right? Like you can't just pick up a burning building.
Not easily, no. So firefighters usually focus on the other two sides, removing the heat or removing the air.
And the most common tool for that is water.
Water. Lots and lots of water. Its main job is cooling. It absorbs a huge amount of heat, bringing the temperature of the fuel down below its ignition point.
Does it do anything else?
Yes, a secondary effect. When the water hits the fire, it turns to steam. That steam helps push away or displace the surrounding air, slightly reducing the oxygen supply, too.
Water isn't always the answer, is it? The sources mention some big limitations.
Crucial limitations, especially today. Two big ones. First,
Electricity.
exactly. Water conducts electricity. Spraying water on a fire involving live electrical equipment is incredibly dangerous, potentially lethal for the firefighters.
Okay, big problem number one. What's number two?
Oil and petrol fires. Think about a kitchen grease fire, or worse, an industrial fire with flammable liquids. Water is heavier than oil or petrol.
So if you spray water on burning oil,
The water sinks right through it. The burning oil or petrol just floats on top of the water and keeps burning. You haven't cooled the fuel and you haven't cut off the air. Water can actually spread the fire in that case.
right, I've heard that. Never use water on a grease fire. So if water is out for electrical fires and for oil or petrol fires, what's left?
The go-to is carbon dioxide, CO2.
CO2 extinguishers, those red cylinders you see everywhere. But CO2, isn't that like way more complex and maybe expensive than just hooking up a hose? Why is it the standard?
It's the standard because it's incredibly effective for those specific types of fires thanks to a brilliant dual action. First, CO2 gas is much heavier, much denser than oxygen.
Okay.
So when you discharge that CO2 extinguisher, the gas flows out and settles over the fire like an invisible blanket. It physically pushes the oxygen away from the fuel.
It smothers it, cuts off the air supply, just like the blanket on burning clothes earlier.
Exactly. That's the primary action. But there's a bonus.
A bonus.
Yeah. CO2 is stored in those cylinders as a liquid under very high pressure. When you release it,
It expands rapidly.
enormously. And that rapid expansion causes a dramatic drop in temperature. It gets incredibly cold almost instantly, like a burst of refrigeration.
Ah, so it also cools the fire down.
Yes, it provides a significant secondary cooling effect, helping to bring the fuel temperature back down below ignition, smothering and cooling. Plus, it generally doesn't damage sensitive electrical equipment like water would.
That is very clever.
Mm.
A two-pronged attack. Smother and cool.
And it's fascinating, isn't it? Because the CO2, our best friend for certain fires.
Is the exact same gas we're going to talk about later in terms of climate change issues.
That tension is definitely something to keep in mind. But before we get to the environmental impact, let's connect this back to that initial puzzle. The candle flame versus the coal glow.
Right. Why the difference?
It comes down to vaporization and the structure of a flame.
Okay. Vaporization, meaning turning into a gas.
Precisely. Substances that produce a visible flame are those that turn into a gas or vaporize when they burn. Think about kerosene or the wax in a candle. As it melts, the liquid wax travels up the wick and gets hot enough to vaporize. It's the wax vapor that's actually burning in the flame.
Okay, so wax vapor burns. What about coal or charcoal?
Charcoal is mostly pure carbon. It doesn't readily vaporize when heated. It just reacts directly with oxygen on its surface. So you get heat and light, that red glow, but no distinct flame structure because there are no burning vapors rising up.
Uh-huh. So flame requires fuel vapors. No vapors, no flame, just a glow.
You got it. And understanding that vaporization happens helps us understand the different parts, the different zones within a candle flame itself. There are actually 3 distinct regions.
3 zones. Okay, let's break that down, starting right near the wick.
Right at the base, touching the wick, you have the innermost zone. It looks dark, almost black,
Why black?
because it's full of unburnt wax vapors. The heat from the flame is vaporizing the wax, but oxygen can't really get into this core area, so no combustion is happening there yet. And because there's no burning...
It's the coolest part.
Exactly, the least hot part of the entire flame. Mostly just hot wax gas waiting to burn.
Okay, moving outwards from the black zone.
We get to the middle zone, the big, bright yellow part. This is what we usually think of as the flame. It's luminous.
Luminous meaning it gives off light. Why yellow?
This is where partial combustion happens. There's some oxygen mixing in, but still not enough for complete burning. This incomplete combustion creates tiny, unburnt particles of carbon. Basically, yes, these tiny carbon particles get extremely hot and glow brightly, giving off that characteristic yellow light if you stick a cool glass slide into this part of the flame for a second.
You get that black ring of soot deposited on it.
Precisely. Proof of the unburnt carbon. This zone is moderately hot. Hotter than the inner zone, but not the hottest.
Okay, so inner black zone, coolest.
Hmm.
Middle yellow zone,
Yeah.
moderately hot, partial combustion. What's the last zone?
The very outer edge, it's often faint, sometimes looks slightly bluish, and it's called the outer zone or the non-luminous zone.
Non-luminous, so not much light.
Very little light compared to the yellow zone. But this is where the complete combustion happens. The fuel vapors here have full access to the oxygen in the surrounding air.
Everything burns completely.
Right, and complete combustion releases the maximum amount of energy. So this thin outer layer is actually the hottest part of the flame.
The hottest part gives off the least light. That seems counterintuitive.
It does, but it's true. Think about a Bunsen burner flame. The roaring blue flame is much hotter than the yellow safety flame. Same principle.
And this difference in temperature within the flame, it has practical uses, right?
Absolutely. Goldsmiths know this well. When they need to melt gold or silver, they use a thin metallic blowpipe.
Yeah, I've seen that. They blow air through it into the flame.
And they direct the very tip of that outer, non-luminous, bluish part of the flame onto the metal. Why?
Because that's the hottest part. Gets the metal up to melting point faster.
Exactly. They leverage the structure of the flame for maximum efficiency.
Speaking of efficiency, that leads us perfectly into the next bit. Fuel quality and, well, the consequences.
Right. What makes a good fuel? Ideally, you'd want something cheap, easy to find, easy to burn.
Burns at a steady rate, not too fast, not too slow.
Produces a lot of heat for the amount you use, and this is key, leaves behind no nasty residues or pollution.
But the sources are quick to point out. That perfect, ideal fuel.
Doesn't really exist. Every fuel has trade-off, so we need a way to measure how much bang for your buck you get in terms of heat.
And that measurement is...
Calorific value. It's the standard measure of fuel efficiency.
so defined.
It's the amount of heat energy released when you completely burn 1 kilogram of that fuel. The unit is typically kilojoules per kilogram, or kJ/kg.
Okay, kJ/kg. Higher value means more heat per kilo.
Exactly. More efficient fuel. And the numbers really tell a story. Look at traditional fuels. Cow dung cake.
Pretty low, I bet.
Very low, only about 6,000 to 8,000 kJ/kilograms. Wood is better, maybe 17,000. Coal gets up to maybe 25,000 to 33,000.
Okay, so coal is way better than dung or wood.
Hmm.
But how do modern fuels stack up? Like LPG, the gas in cylinders for cooking.
Now we're talking. LPG hits around 55,000 kJ/kilograms. Much more energy packed in there.
Wow, almost double coal. And what about things like maybe hydrogen? People talk about that as a future fuel.
Hydrogen is off the charts. Its calorific value is enormous, around 150,000 kJ/kilogram. That's why it's so attractive from an energy perspective, though storage and production are challenges.
Okay, so we chase higher calorific values for efficiency. But burning all this fuel, especially as global consumption rises, it has downsides, major ones.
Huge downsides. The sources highlight 4 major harmful effects we really need to grapple with.
Let's take them one by one. What's the first?
It relates to incomplete combustion, which we talked about with the yellow flame zone, burning carbon-based fuels like wood, coal, petrol, if it's not complete.
It releases unburnt stuff.
Unburnt carbon particles, basically fine soot. These tiny particles get into the air we breathe. They're pollutants.
And what do they do to us?
They're dangerous. They can cause serious respiratory problems. Think asthma, bronchitis. Prolonged exposure is really bad for lung health.
Okay, so soot from incomplete burning is problem 1. What's 2?
Also related to incomplete combustion, when there's not enough oxygen, instead of producing just carbon dioxide, CO2, the fire produces carbon monoxide, CO.
Carbon monoxide, that sounds bad.
It is. CO is a highly poisonous gas. It's odorless, colorless. You can't detect it easily.
And this is why they warn you.
Never burn coal or charcoal or even run a generator inside a closed room or tent. As the oxygen level drops, the combustion becomes incomplete and deadly levels of CO can build up silently. It's a killer.
Scary stuff. Okay, so problems 1 and 2 are from incomplete burning. What about when combustion is complete? We get mainly carbon dioxide, CO2, right?
Right. And that leads to the third major consequence, global warming.
Ah, the big one.
CO2 itself isn't poisonous like CO. We exhale it. Plants need it. But burning massive amounts of fossil fuels releases huge extra quantities into the atmosphere.
And that acts like a blanket around the Earth, trapping heat.
Essentially, yes. Increased CO2 concentration leads to a gradual rise in the Earth's average atmospheric temperature, the greenhouse effect amplified.
And the consequences of that warming are, well, we hear about them all the time.
Melting polar ice caps and glaciers, rising sea levels, which threaten coastal cities and communities.
Yeah.
More extreme weather events. It's a global crisis driven largely by our fuel combustion.
Okay, so unburnt carbon, poisonous CO, climate-changing CO2. Is there a fourth one?
Yes, acid rain. This comes from impurities often found in fuels or from reactions at high temperatures.
Like what impurities?
Burning coal and diesel often releases sulfur dioxide, SO2, because there's sulfur in the fuel, and petrol engines, operating at high temps, produce gaseous oxides of nitrogen, NOx.
And these gases go up into the atmosphere.
Where they dissolve in rainwater, forming sulfuric acid and nitric acid. When that rain falls.
It's acid rain, which damages what?
Crops, forests, lakes. It can kill fish. It also corrodes buildings and statues, especially those made of marble or limestone. And it damages soil chemistry. It's another widespread environmental impact.
So 4 big problems. Respiratory issues from soot, poisoning from CO, global warming from CO2, and acid rain from SO2 and non-tox. That's quite a list.
It is, and it highlights why there's such a push towards cleaner fuels. For example, switching vehicles in cities from diesel and petrol to
CNG.
Yeah.
Compressed natural gas.
Exactly. CNG still produces CO2 when burned completely, so it's not perfect for climate change. But it burns much more cleanly than petrol or diesel. It produces far fewer of those harmful soot particles, CO, SO2, and NOx.
So it's a step in the right direction for air quality, even if the CO2 issue remains.
It's considered a significant improvement, yes. Understanding the chemistry forces us to confront these trade-offs and the long-term consequences of how we generate energy.
So wrapping this up, we've gone from the basics, needing fuel, air, and that critical ignition temperature, to the structure of a flame itself. Remember that outer non-luminous zone?
The hottest part, used by goldsmiths.
Right. And we saw how CO2 extinguishers work with that amazing dual action, smothering and cooling, making them vital for electrical and oil fires.
But we also landed on this deep, almost paradoxical tension. CO2, the chemical we rely on to put out dangerous fires,
is the same chemical whose buildup in the atmosphere from burning fuels is driving global warming, potentially leading to massive environmental changes like floods from melting glaciers.
It puts us in a strange position. The tool for immediate fire control is contributing to a potential long-term loss of control over our environment, including water levels.
So here's something to think about. We have this one chemical, CO2. It's essential for fighting certain fires right now, but its accumulation causes potentially catastrophic future problems, including flooding. Where should the priority lie? Reducing the CO2 emissions from burning fuel in the first place, or focusing on better ways to manage the consequences, like fire containment and maybe even flood defenses, accepting CO2 as part of the picture? It's a tough balance when the same molecule plays both hero and potentially villain.
A critical question for our energy future.
Definitely something for you to mull over. Thanks for joining us on this deep dive. Until next time.